Okay, so I'm going to make a conceptual video on something called U-substitution. U-substitution is an integration technique. And what I want to do in this video is I'm not going to tackle any crazy U-substitution problems, but what I'm going to do is try and establish a really deep understanding of what it is, why we can use it, why is this even legal, and exactly how you could theoretically go about doing it. And at the very end, I'll go through maybe a very elementary example or two, just so you can see it at work at its simplest level. So we're going to go back to derivative world for a few minutes in order to get an understanding of what U-substitution is. So if I have some function f of u, and I'm going to make a little note here that u is a function of x. So if I want to take the derivative of both sides, or take the derivative of this function with respect to x, that's going to equal df du, so just taking the derivative of this chunk right here and multiplying it by du dx. If this doesn't make sense, you're going to want to go back and review the chain rule. But essentially what you're saying is that, if I have one outer function and one inner function that's a function of x as well, then all I need to do is take the product of those two derivatives, and I will get myself I will end up with something like this. So with that said, this is my chain right here. That's the chain. And so if I have something like sine of, well, no, I won't use a trig example yet. Something like x squared plus 3 all to the 5th power, my f of u would be u to the 5th power. And then my u of x would be x squared plus 3.
So,
whoops, hold on. Sorry, other video finished rendering. Okay, so f of u is u to the 5th, and u of x is x squared plus 3. And so f of u is x squared plus 3 to the 5th. That's f of u right here. But u is also a function of x. So we have this kind of, we're linking things together. And so when you take a derivative of something like this, you end up with this, a function with respect to the inside, with the derivative with respect to the inside, which exists pretty regardless of what's inside it, and then you deal with the outside. So what we end up with here is that you can multiply both sides of this by dx and integrate both sides, and what we end up with is that f of u is equal to the integral of this original derivative, which would be f prime of u times du dx times dx. And mentally in your head, you can kind of see that you can cancel those out, which is slightly shady, but when it gets down to it, those two are perfectly equivalent. And so you can think of dx over dx as being 1, so don't worry about that. So f of u is now the integral of f prime of u du. I mean, that makes sense. That's the definition of integration. But if we have f of u, and I'm going to write this x in now, where x is, ultimately our variable here is x. U is just kind of like a placeholder for something larger like this. So f of u of x is equal to the integral of f prime of u of x times du dx times dx, because this is in terms of x. This might sound kind of funky here, but hopefully this is going to become more concrete very momentarily. Essentially is what happens when you take the derivative of a composite function like this, where you have, x squared plus 3 jammed inside something like u to the 5th. You get this remnant of the original function here. It's had its derivative taken, and it spills out onto the side here, this du dx. And so when you're u substituting, you're being kind of like a detective. You see something that has its derivative taken, and you see what happens when you take the derivative of a composite function, which is the chain, and you're trying to reconcile those two into the original function. It's kind of like if you saw a guy here, and he only had one arm, and then over next to him, you saw an arm. Maybe when you take the derivative of a man, his arm falls off. I don't know, maybe when you take the derivative of a man, he changes into a woman, and his arm falls off. So if you see a woman with her arm falling off, then you know that that was probably a man that had his derivative taken. A very sad life for a man, I suppose. And it's kind of the same thing. When you take the derivative, you're taking a function and you're spilling its guts out and chopping its arms off and belittling it to its most fundamental levels as you take more and more derivatives. And what you're doing when you're u substituting is you're trying to put these pieces together and package them up so that you can tell what used to be, which was this guy. So I'm going to do this now with this function up here. I'm going to say we want to evaluate the integral of 2x times x squared plus 3 to the 5th dx. So what I see right now is this chunk all raised to a 5th power. I'm going to refer to this as a chunk on the inside. So it's a chunk raised to the 5th power, and it looks like we might have some remnants, some arms sitting out here on the side. And so what we're trying to figure out is what this poor function that's been ripped apart used to be before it had its, insides taken out. Well, we're speculating. This is just a speculation that maybe, this can be viewed as a u. Maybe we can call this u. And this is just kind of, it's not arbitrary. There's logic behind it. But in mathematics, if you say 2x minus 6 equals 5, and I want to say, let's call theta equal to 2x, then I can write theta minus 6 equals 5. Don't feel like you're bound to these rules and procedures, because you're not. You obviously have to be legal about things, but redefining a new variable and calling it something else and using it in the place of some other variables or some more convoluted chunk of variables is completely legal. So let's deal with this now. We're going to say that, and when you take the derivative of a function like this, this all hinges on the fact that when you use the power rule and bring this down and reduce the power by 1 and then multiply it by, 2x over here, this remains unchanged. And then it gets its derivative taken. So if this part remains unchanged, then this u, what we're calling u, is probably there in the original function. So right now we're speculating that this original function might have an x squared plus 3 in it somewhere. So now what we have is the integral of 2x times u to the 5th dx. Now, obviously, this is a little unsettling because we have a u here and x is here. But look at this form right here. We're saying f prime of u of x times du dx times dx. So if this is dx, then if this is du dx, then we're good to go. All we need to do is integrate this new function that we've established in order to recover our f of x. So let's say u equals x squared plus 3. I'm just doing this because I think it's going to be useful. A lot of the time, that's what math's about. I'm going to take this derivative with respect to x. So say this function did have its guts spilled out when you took its derivative earlier. What would those remnants laying on the sides here be? So I'm going to take the derivative with respect to x because I can. Du dx equals x squared plus 3. No, it doesn't at all. What am I doing? Du dx equals 2x. Just using our power rule here. So we're saying if this was part of our function and we took its, we took this poor function's derivative, then it would have had to have had a chain somewhere. And that chain, because of what's on the inside, would have had to have been 2x. So du dx is 2x in this case. This can be viewed as du dx. Check that out. And then we have our dx here, which is right here. And another way to view this, you can write du equals 2x dx. And that's exactly what we have. We have 2x dx, even though it's shuffled around a little bit. So that, once we reconcile this, that is du. And all that is now is the integral of u to the 5th du. And we know how to deal with that. No more x's. Forget the x's exist. We've packaged them up into this, into these nice little blobs of u that we can ship around now. And so that is going to be equal to 1/6 u to the 6th plus c. Plus c. Well, we probably don't want to give our answer in terms of u, because whoever, is reading whatever we're writing doesn't know what u is necessarily. One part of mathematics, mathematics is a language, and you're supposed to use it to try and communicate your logic to people. And if someone reading it can't understand what you're doing, then you're not doing your job very well. So this is also equal to 1/6 u is x squared plus 3 to the 6th plus c, our random constant. And so that is the solution to this problem. And hopefully through this, you've seen that, if this is our original function and we take its derivative, the power comes down, so we get 6/6 x squared plus 3 to the 5th. This is untouched. We have not touched that yet. And then we multiply it by 2x. That's 1. And that's our 2x here. And that's exactly what we started with. So when you're integrating something, when you take derivatives over and over again, you just leave this little trail that you have to investigate. And once you catch a lead that, if you take this thing's derivative, it'll be similar to something on the outside, or in this case, exactly the same, then you're onto something, and you can start packaging things up into u and its derivative in order to reconcile the original function. So hopefully that allows you to gain a better understanding of what u substitution is, kind of how you do it, and what the motivation is for doing it. Thanks for watching.